Karen Koch from Unicia High School, and I'll be doing a revision on organic reactions with you. So for starters, we are going to just work through the summary as provided to us by the Free State Department of Education, and then from there onwards we will deal with some exam questions. So if we look at the different types of reactions that alkanes can undergo, we classify them into substitution or combustion, also called oxidation and elimination reactions. So for the substitution, for example, we've got methane that will react with a halogen. So we've got two reactants here, and then one of the hydrogens being substituted by one of the halogen atoms. That's why it's called substitution. And then again, one of the halogens being substituted by one of the hydrogens. So we end up with two products again, therefore called substitution. Started off with two chemicals, ended up with two chemicals. And our reaction conditions is that this reaction does not take place spontaneously. It needs heat or sunlight to react. The next one is the reaction with oxygen or oxidation, also called combustion. So this is the burning of the alkanes, and this is also true for the alkenes and the alkynes. All your hydrocarbons will burn in oxygen, and what makes this easy is the fact that you will always get carbon dioxide and water molecules and a lot of energy, and the balancing is simple because you simply balance the carbons first, and then the hydrogens, and then the oxygens. Always getting carbon dioxide, water, vapor, and energy. Then elimination, which is also known as thermal cracking. This is where a long chain alkane, longer than the one illustrated here, but a long chain alkane is broken down into smaller, more usable portions because your very long chains aren't usable. So broken down into smaller, more usable portions. In this case, an example just of a pentane being broken down into an alkane with 3 carbons, and then your alkenes got the rest of the number of carbons, so 2 more. So you will always end up with an alkene and an alkane, or you will end up with an alkene and hydrogen. It depends on where you do the cracking. The conditions here is that you need heat and very high pressure. It's not a spontaneous reaction. Then the reactions of the alkenes. When alkenes react, we call it in general addition. And now it depends on what you are going to add to the alkene so that it's got a specific name. Addition called halogenation is when a halogen has been added, and as you can see, the double bond simply splits open and a chlorine diatomic molecule gets added there. So we start off with an alkene and we end up with a haloalkane, and you do not really need any special conditions because this reaction is spontaneous. Then we get the addition of hydrogen. In this case, we do need a catalyst, and your catalyst can either be platinum, palladium, or nickel, and we end up with the corresponding alkane. This is also known as hydrogenation, and this is the reaction that gets used to change polyalkenes into the corresponding alkanes, so to turn your plant oils into margarines. That's the process that takes place there. Then some more reactions of the alkenes. You can also add a water molecule. So once more, the double bond splits open, and you add the hydrogen and an hydroxide group or hydroxyl group, hydrogen and hydroxyl group being added. And how does it get added? It gets added in such a way that the hydrogen atom bonds to the carbon that already has the greater number of hydrogen atoms, and that's the only product that gets formed there. And your conditions is you need an excess of water and then also a small amount of acid as catalyst. Then another addition is if you've got a hydrogen bonded to a halogen, so hydrohalogenation, and the conditions is you may not have water, because if you've got water, you're going to get the alcohol again. Now you've got no water, so you are adding hydrogen bromide in this case. Again, where does the hydrogen bond? It bonds to the carbon that contains the bigger number of hydrogen atoms, just to differentiate between which products get formed. Then for the haloalkanes, the elimination, in other words, now we are removing. And we are removing, in this case, hydrogen bromide, and we are heating it up. So the conditions is you need a concentrated, strong base. So strong base being a group 1 base, sodium hydroxide, potassium hydroxide, lithium hydroxide, in ethanol with heat. And the moment that you add the heat as well, you totally remove the hydrogen bromide from the solution. You end up with an alkene. The one where the major product is the one where the hydrogen atom is removed from the carbon with the least number of hydrogen atoms. So the most substituted double bond forms. In other words, a double bond with the most alkyl groups. And your reaction conditions, once more, heat and concentrated strong base in ethanol. Then the reactions of the haloalkanes, in other words, this is now an alkane with a halogen atom added to it. So we are now reacting it again with a strong base, but this time it is a dilute strong base, and we are adding only mild heat, not extra heat. And in this case, you do not get the total removal of a molecule. You simply get substitution. So the Br group gets substituted by the OH group. So you end up with an alcohol. You could also, instead of having the dilute strong base, you could have had an excess of water, again with mild heat. And once more, it's substitution of the halogen with hydroxyl. The reaction of the alcohols, again, if we use a dehydrating agent, and you should know from the reaction in the formation of the esters that sulfuric acid is a dehydrating agent. So we are removing water, which means you're going to remove OH, the hydroxyl. And now the question is it now that H or that H that goes with it? And it is the hydrogen on the least substituted carbon, so the double bond forms between carbon 2 and 3. Our conditions is the dehydrating agent and heat. Then also, if we have an alcohol and we react it with a hydrogen halide, then we end up with a hydroxyl group being substituted by the alkane and water as our second product. Esterification, we're familiar with the carboxylic acid, COOH, with an alcohol, and the hydroxyl group and hydrogen from the ion reacting, your dehydrating agent being sulfuric acid, and you end up with an ester and a water molecule. Okay. Right, so here we've got a question that says, in the flow diagram below, X, Y, and Z represent 3 different types of organic reactions. P represents an organic compound, which is necessary to mention because sometimes the products are inorganic, or some of the products. Okay, so we are looking at reaction X, and they ask, name the type of reaction represented by X. And we've got a haloalkane, which turns into an alkene. And you can simply just learn off by heart. When I change from a saturated compound into an unsaturated compound, the general reaction is elimination. If I want to see or name it in specific which type of elimination, I need to remove a molecule. And it's easy for us to see that Br is one of the atoms that's been removed, and then as well the H. So there's an HBr being removed. So being removed means I've taken it away, so the term that we give to it is dehydrohalogenation. It's hydrogen and a bromine that's been removed, so it's D, taking away hydrogen and halogen, dehydrohalogenation. So the type of reaction, elimination or dehydrohalogenation. State 2 reaction conditions needed for this. To remove, we need extreme, and the extremes are heat, strong heat, and then also another one that we need to add when we are reacting with the haloalkanes is concentrated strong base. Concentrated strong base. Sometimes you don't need a concentrated one, just a strong base, but because we're removing, we're using concentrated strong base. Question 3, reaction Y represents a substitution reaction. Write down the structural formula of compound P formed in this reaction. So in reaction Y, we are substituting KOH and mild heat. And this is what I've just said. For this reaction where I've completely removed H and Br, I needed a group 1 base, which was maybe potassium hydroxide as they've got here, but I needed a concentrated one and strong heat. Now I'm using the same chemical, but now it's mild heat. So now it means that we are not removing, we are simply substituting. So I redraw that formula. So therefore, for question 5.1.3, I am redrawing CH3, CH2, CH3, CH3, and the Br is now the part that's going to be substituted by part of the KOH, and the part that we replace, we are all familiar with, is OH. Write down the structural formula of compound P. So that would now be compound P. Now question 4. Apart from the organic reactant, write down the name or formula of the other reactant needed in reaction Z. Now let's see what happens in Z. In Z, we've got an alkene, and we want to end up having an alcohol. And they said apart from the organic reactant, which is this one, we want to end up with this one. What do I need to add? So I need to add something that will give me a hydroxyl group, and the chemical that we then need to add is water. Right? So we are going to add water to it. Question 5, name the type of reaction represented by Z. So in Z, look what I've done. I've taken away a double bond, and I have added water, which means addition. Your reactions of your unsaturated compounds turning into saturated compounds will be addition. Your reactions of your alkenes, usually called addition, and because I have added water, I may also call it hydration. Let's look at another question. It says, some of the reactions of butane 1-ol are represented in the flow diagram below. Q and R represent the organic products formed. So my first advice to you will be, when you get any question like that, before you even start to try and answer the questions, is to simply do the structural formula. So for butane 1-ol, I know for butane there are 4 carbons, and then 1-ol means the hydroxyl group is on carbon 1, either being this one or that one. So the rest of the bonds completed by hydrogen. So this was not asked, but in looking at this, it's maybe easier to answer the questions. So first question, is butane 1-ol a primary, secondary, or tertiary alcohol? So now you also know the answer to that, because these terms refer to the number of carbon atoms attached to the carbon atom that contains the hydroxyl. So this carbon contains the hydroxyl. It is linked only with one other carbon, making it a primary alcohol. If the hydroxyl was on this carbon would have had a neighbor carbon on that side, and on this side that would have made it secondary. And tertiary we only get if there are alkanes with, or alcohols with branches. Product P is formed when butane 1-ol is heated in the presence of concentrated sulfuric acid. So write down the name of the type of reaction that takes place. Now, you should now know by now, the moment that we react with sulfuric acid is a dehydrating agent. So the type of reaction will be dehydration, and dehydration means you are taking away a water molecule, and if you're taking away a water molecule, you are then also doing some sort of elimination. So you can call it either elimination, or you could call it dehydration. So I'm removing a water molecule. And now they ask for the balanced equation for the reaction that takes place using structural formulae. So I am starting with the butane 1-ol. That's the one that I've been given. Structural formula. And the sulfuric acid is my dehydrating agent, and the fact that I do not need to, it is a catalyst in this reaction, so I do not need to acknowledge it in my product. Therefore, I simply put it on the arrow. And now I've got hydrogen, and I've got my 4 carbon atoms. And I have to remove water from it, which means OH goes there, and if OH goes, then that bond becomes a double bond there, and now I just need to ensure that I am left over with the correct number of bonds on my carbon. So OH removed from there, H removed from there, and that then gives me this one, which in name would be but 1N. Question 5.3. Product R, so let's go back. Product R, look at product R. It was butanol, and you've reacted it with ethanoic acid. So product R is formed when butane 1-ol reacts with ethanoic acid in the presence of an acid catalyst. Write down the name of the type of reaction that takes place. Now we know it's esterification, and the structural formula of the organic product formed. So it is up to you to decide whether you want to draw the formula of the alcohol first, or whether you first want to draw the formula of the acid. If we draw the alcohol first, remember there are 4 carbon atoms. And now we had OH here. And then for the acid, we had ethanoic acid, and then I find it easier to write the mirror image of the acid because we usually put the carboxylic group on the right-hand side. So for this type of reaction, I find it easier to do this, to turn it around. So that would now be ethanoic acid. And then when I combine the two, they did not ask for the full equation. You need to read very well, because they asked for the structural formula of the organic product. I am not supposed to write these 2 separate ones. But I find it easier to do it like that, and now I do the bonding. So I will remove the hydroxyl group and the hydrogen. So that would have been the water, forming the water, and simply where they've been removed, this is now where these 2 molecules form a bond. So I'm now just going to draw a longer bond there. So this is my structural formula of the organic compound formed. Let's just quickly see. I did not add all the hydrogens to this 4th carbon. So there we've got. Okay, and then they didn't ask for it, but if we look at the name, we've got 4 carbons, butanol. So in the name that we have to write here, it would be butyl, because it's an alkane without its last hydrogen, so that makes it butyl. And there are 2 carbons, and that would have been ethanoic acid, so it becomes ethanoate. And now remember, this is the only organic compound that where the name is written as two separate words, and you get penalized if your spelling is wrong. So this would be butyl ethanoate. There is another question. When HBr now reacts with butane 1-ol compound Q, a haloalkane is formed. Write down the name of the type of reaction that takes place. So what happens? Butane 1-ol becomes a haloalkane. Okay, so butane 1-ol becomes a haloalkane. So what happens here is, if you find this confusing, I find it easy to look at the thing that makes it different from being an alkane. So here I've got butane 1-ol. So this makes it different from being an ordinary alkane. And the question said it reacts, it forms a haloalkane. So this means the hydroxyl group needs to be replaced by a halogen. So the hydroxyl group needs to be replaced by a halogen. So that means I need to react it with something that has a halogen in it. So we are looking here. So what type of reaction is this? This is going to be substitution or hydrohalogenation, being the specific type of substitution. IUPAC name of the haloalkane formed. So first of all, I redraw my alcohol. This is what I had. And now I have to add HBr. And so what gets changed? This part gets substituted by Br. So what is the name of this haloalkane that's formed? The Br replaces the OH. So this becomes 1-bromobutane. Why 1? Because it is on carbon 1. Right. That is the same question. So here we are on a question that was asked in November 2009. So we've got butane 2-ol. It undergoes dehydration, which means water molecule being removed, and two compounds are being formed. So let's first of all just write the compound. So we've got butane 2-ol. So that is 1, 2, 3, 4. And on carbon 2, the hydroxyl group. If I go back to the question, it says butane 2-ol undergoes dehydration and I get two compounds. Okay, so let's look at dehydration. Dehydration means take away what? Water. So I want to take away water. And this then means that I can now take away this hydroxyl group with this hydrogen, or this hydroxyl group with that hydrogen. And it depends on which hydrogen I'm going to remove, which one of the two products I get. So if I remove these two first, let's just write down our product if we remove these two. So let's do the two green ones there. So I'm going to end up with once more 4 carbon atoms, hydrogens all the way, and we've now removed this OH and that H, and that means that carbon 2 and carbon 3 will have lost an atom each of them, so therefore the double bond sits over there. And then the other alternative is if I do the blue ones. So that would give me once more 4 carbon atoms, each carbon being 4 valent, right? And I've now removed the hydroxyl from carbon 2 and the hydrogen from carbon 1, and that would then leave me with a double bond there. So dehydration is a type of elimination. I'm removing. When I'm removing, I end up with an alkene. So 2 products. And they will have two different names, of course. Both of them would be butene, but I have to specify where is the double bond. So in this one, it would be but-1-ene, and this green one would be but-2-ene. And one of them is a major product, and the other one is a minor or a secondary product. And how do we know which one is which? And the answer to that is that you always remove the hydrogen from the carbon that is least substituted. Now, what does that mean? It simply means if I look at this carbon here, this carbon had 2 hydrogens. This carbon had 3 hydrogens. So it was most substituted. So this one would be the minor product. This one that had 2 will rather lose its hydrogen, so this would be the major product. Another way of looking at it is, if you look at this molecule around the double bond, it looks like a symmetrical molecule, whereas this one is not symmetrical. So again, this is the minor product, that is the major product. Right, now we've done all of this, but we still haven't looked at the questions. It said, name the type of organic reaction of which dehydration is an example, and we know it's elimination. To which homologous series do compounds P and Q belong? The alkenes. What type of reaction takes place when compound P is converted to compound X and Y as illustrated? Now, if I now look at P, I get X and Y after its reaction with HBr. So now I need to look at compound P, and compound P can form 2 products. So if I look at these 2 compounds, I need to add HBr, and I need to get 2 products. Okay? So to be able to answer that question, I have to add HBr, and HBr will be added at the double bond. If I add H here and Br there, I'm going to get 2-bromobutane. If I add Br here and H here, I'm going to get 2-bromobutane again. So that means that this cannot be compound P. So then this one has to be compound P. So if I now add to compound P, in other words, but-1-ene is compound P, now I have to add HBr. So this would mean I could add an H here and a Br there, so I get 2-bromobutane, or I can add H here and Br there, and that would be 1-bromobutane, and that now determines which of these 2 is compound P and which one is compound Q. Just to point out again, if I added H here and Br there, or H here and Br there, I get the same molecule. They are both 2-bromobutane. But that one has got a 1-bromobutane and a 2-bromobutane, so but-1-ene was then, in my original question, compound P. Okay, what type of reaction takes place when compound P is converted to compound X and Y? So we are adding HBr, and the type of reaction is then hydrohalogenation, which is also a type of addition. Remember, an alkene turning to a saturated compound, it's an addition reaction. Use structural formulae to write a balanced equation for the preparation of compound Q as illustrated above. We've already done, we need to do a structural formula to write the preparation of compound Q. Now, compound Q is the one that in our reasoning just now could only form one product with HBr, which means compound Q is going to be our major product, and therefore it would be the formation of this one. So what you would have written was the original butane 2-ol. You are adding, remember it's structural formula, you are adding HBr, and you are ending up with the green one, and that would then be the answer to that question. This would be compound Q. Okay, if I go back, which compound P or Q will be the major product? It would be Q. Give a reason for your answer, and I've already discussed that with you. in our answer, why is this the major product? 2 reasons. It's your more symmetrical molecule. Also, maybe the reason that they would rather want you to write is the fact that the carbon atoms with, the carbon with the least number of hydrogens will be the carbon that loses the hydrogen in the dehydration reaction. So this would be your major product. Then the next question asks, which compound PQ will be the major? This is the same question being repeated. Write down the structural formula and the IUPAC name for compound X. Now this is compound X. This is now after we've added HBr. So we've actually already done it. So let's add HBr. So we are removing the double bond. And we are adding H and Br. And again, I repeat, it doesn't matter which side you add which one because this is 2-bromobutane. Then, I need to go back. If we look at the last question, a learner indicates that he can convert butane 2-ol directly into X. Name the type of reaction that will take place during a direct conversion. So now remember, what is X? X was now the haloalkane. So can you convert an alcohol into a haloalkane? Yes, you can, because it is a saturated compound to a saturated compound. Therefore, the type of reaction is simply substitution. Type of reaction, substitution. Which type of substitution? You substitute the hydroxyl group by a halogen group, so you are doing hydrohalogenation. Right, November 2012. We get to the idea that we are looking for general things. Double bonds being turned into single bonds. In other words, unsaturated into saturated is an addition type of reaction. And then the opposite is true. If you've got a saturated compound turning into single bonds, in other words, unsaturated into saturated, it becomes... Kan jy dit uitsny asseblief? Want ek het myself nou heeltemal hier so in 'n ek het nou vergeet wat ek gesê het. Okay, we can generalize. If we've got an unsaturated compound, in other words, an alkene that turns into an alkane, it means that we need to get rid of the double bond. That means we need to add a whole molecule, so it's addition. And we get different types of addition. You can add water, so it's hydration. You can add a halogen, then it's halogenation. You can add hydrohalogen, then it's hydrohalogenation. And you can add just hydrogen, then it's hydrogenation. Then we can also work from a saturated compound into an unsaturated compound, so an alkane or a haloalkane turning into an alkene, and that is a type of elimination. And whatever it is that you eliminate will give it its specific type of name, like dehydration or dehalogenation. Right, so to get back to this question, the flow diagram below shows how 3 organic compounds can be prepared from 2-bromomethylbutane. Now, once more, my very good advice to you would be to draw the structural formula, but I do see it does get asked in this question, so if that is the case, then you're not going to draw it from starters. So the first question is, write down the molecular series to which 2-bromo-3-methylbutane belongs. Now, remember what we've got. We've got an alkane, the butane, and we've got a halogen. So it is a haloalkane. That is the name of the series. And the next question asks for you to draw the structural formula. And our main chain is butane, which means we start off with butane, drawing the 4 carbons. Then, doesn't matter at which side you start to number it. On carbon 2, there must be a bromine group, so that is Br. On carbon 3, there must be a methyl group, and it's very important to remember that you may not write CH3. It is a structural formula, so the 3 H's must be structures like that. And then each one of the other 4 valencies of each carbon to be filled up with hydrogen atoms. So that was question 5.1.2. Right, question 5.2. Reaction 2 takes place in the presence of a dilute sodium hydroxide solution. Now, we know that we've got 2 reactions with sodium hydroxide or a group 1 hydroxide, which is a strong base. Now, dilute tells me it's not extreme measures. Extreme measures cause elimination, which means you're going to turn the compound into an unsaturated one into an alkene. Now, because we've got dilute, it is simply substitution. So the type of reaction that takes place is substitution. The structural formula of compound B. So I first just redraw the original. You do not need to do this in exam, of course, because you will have this now in your previous answer. The methyl group as separated structural formula. So this is what I had. And to this one, we add sodium hydroxide solution. So remember what we are adding is KOH. And what I told you before, I am looking for the thing that is not a haloalkane. And in my structure here, the not haloalkane part is the bromide part. And the bromide part will be substituted by the hydroxyl part. This means I am removing bromide and I am replacing it with the hydroxyl. And again, structural formula, so do indicate the H. And whether you drew the H there or below it, it really doesn't matter. So structural compound here, so we've now turned a haloalkane into an alcohol. Reaction 1 takes place in the presence of concentrated sodium hydroxide. Now I've got the concentrated sodium hydroxide. Remember the previous one was dilute. Another reaction condition needed for this reaction. So the moment that I've got concentrated acid, it's the extreme one, and remember the extreme one also asks for heat, strong heat. The type of reaction which takes place when I've got the concentrated base and I add strong heat, I am removing. So the type of reaction is elimination. The structural formula of compound A, the major product form. So first of all, I once more start off with my original, simply because I haven't got the other one open. You won't need to waste time like this in exams. Sorry, that's BR. And then here we've got the methyl group. And we are reacting it with a concentrated base. So we are eliminating. So when I am eliminating, I am taking away a hydrogen and the bromine. So this Br is definitely one that's going to go. So away Br goes. Now I need an H. And now remember, there are 2 adjacent carbons. The question is now, do I remove this H, or which is adjacent to the Br, or do I remove that H? And the rule is you remove it from the least substituted carbon. What does this mean? Carbon has got 1, 2, 3 hydrogens. This carbon's got 1 hydrogen and a methyl group, so it's got 2 substitutes. This one's got 3. Therefore, from the least one remains, this is the carbon that needs to go. Therefore, that carbon needs to go. That one will stay. And where the carbon was and the Br was, I'm now left over with a double bond. So this is now the structural formula for your major product. You will get a minor product with a double bond there, but not major. This is the major one. We now look at reaction 3. Reaction 3 takes place when compound B is heated in the presence of concentrated sulfuric acid. Now remember, if we go back to what we've done, compound B was the alkane. So we had HC, need to redraw it again, because we've reacted the Br with a mild, with a dilute base, therefore the Br was simply substituted by OH, and then we've still got the methyl group here. And the question now says, now we react this one in the presence of concentrated sulfuric acid. It's heated in the presence of concentrated sulfuric acid. Once more, with concentrated sulfuric acid, you've got two reactions. The one is if you add an alcohol with a carboxylic acid. So here we do have an alcohol, but we do not have a carboxylic acid, therefore we do not do esterification here. Now the only other one between your alcohol and having concentrated sulfuric acid is where we use the acid as the dehydrating agent. So now the sulfuric acid needs to remove water from it. Therefore, I'm going to remove OH, and I need to remove H. And again, the question is which H, this one or that one? So the least substituted one, so I am removing this H. Therefore, the product that gets formed would be H2O, and there where I've removed those two chemicals, I end up with the double bond. So that is the product that will form, and I now need to write down the IUPAC name of this product. So we have to count 1, 2, 3, 4. So there are 4 carbons in the main chain. That makes it bute. Oh, sorry. Bute. There is a double bond. It makes it ene. I need to say on which carbon is the double bond. Now, if I count from this side, it's on carbon 2. If I count from this side, it's on carbon 2. So it's bute 2-ene. And then I simply need to add where is the methyl group. And because it doesn't matter from which side I've numbered to get my actual series name, the alkene, numbered as carbon 2, then I will now number from the side which will give the substitute here, or the side chain, the smallest number, and that is then on carbon 2. So this will be 2 dash methyl, one word, bute 2-ene. Right, and that then ends our session on revision on organic reactions.